So now let's have another solved example on the transformer. So we have a three-phase transformer, 50 hertz three-phase, 50 hertz transformer with a delta connected primary and star connected secondary. So the primary delta, secondary is a star connection. The line voltage being 22 kilovolt and 400 volts. So the line to line voltage here 22 kilovolt and the line to line voltage here 400 volt. The secondary has a star connected balanced load, so it is has the same resistance and inductance or the same impedance Z. This impedance equal to this one equal to this one. This means it is a balanced load. If these values are different from each other, it will be unbalanced load. So it is a secondary with a balanced load at 0.8 power factor lagging. We will understand how can we use this later in the problem. The line current on the primary side is 5 ampere. So the line current here of the delta is 5 ampere. So the phase current will be 5 divided by root 3. Okay, find the current in each coil of the primary and the secondary line, and what is the output of the transformer in kilowatt. So the first part, which is the current, so we have the line current equal 5 ampere of the primary, and the phase current of the primary will be 5 ampere divided by root 3, right? So the phase voltage on the primary side is equal to 22 kilovolt. 22 kilovolt, which is equal to the line to line voltage of the primary. You can see line to line equal to the phase voltage. And for the secondary here, we have the line to line voltage equal to 400 volt, which means that the phase voltage here will be equal to 400 divided by root 3 as we learned. So from these two values, 22 kilovolt phase voltage of the primary and 400 divided by root 3, which is the phase voltage secondary, we can get the turns ratio. Okay, so the phase voltage on the secondary, 400 divided by root 3. So from here we can get the turns ratio. You can see N2 over N1, N2 over N1. So it will be like this, N2 400 divided by root 3. And 400, this is divided by 22, so it will be like this, multiplied by 22 kilovolt. So in summary, it will be 400 divided by 22 kilovolt multiplied by root 3. So it will give us this value. You can see here that the definition of turns ratio, it changes from one reference to another. So we have some reference says that the turns ratio is equal to N1 over N2. And in this problem, for example, it is the turns ratio which is denoted by K. K here representing the turns ratio from another reference. It is equal to N2 over N1 or V2 over V1. So it depends on the reference itself. Okay. So we have this turns ratio. Now, how can we use this turns ratio? First, we will get the primary phase current. So the primary phase current is this current here. Okay, so the phase secondary current, what's the value of the phase secondary current, which is the secondary line current? They are similar to each other. So the secondary phase current, I phase 2, will be equal to the primary phase current 5 divided by root 3. Okay, this is the phase of the primary, I phase 1, divided by what? Divided by the turns ratio K, divided by K. Why? Because here, as you can see, this ratio is N2 over N1, right? So in order to get the secondary voltage, it will be primary multiplied by this ratio. However, for the current, it will be the primary current or the phase primary current divided by the turns ratio, K. So it will give us finally like this. So as you can see, 5 over root 3 divided by K give us 275 ampere. So as you can see, in order to make sure that you are solving the problem correctly, you will see that if you look here carefully, that we started with 22 kilovolt as a phase voltage. Then since this one is a step down transformer, you will find that the phase voltage became 400 divided by root 3. So the voltage is reduced. So the current should increase, right? Since we have the same power. So you will see that we started with 5 over root 3 ampere for the phase current. Now at the secondary side, we have 275 ampere. So the current increased. So we are solving the problem correctly. Okay. So what is the next step? So we obtain the primary phase current, secondary phase current, which is similar to the line-to-line current. Now we need to find the last thing, which is the power. So you can see secondary line current similar to the phase current. They are similar to each other, line current and phase current. Now let's get the output power in what unit? Kilowatt. Remember, kilowatt. So power in general is equal to 3 multiplied by V phase multiplied by I phase. Okay, this gives us the apparent power S. However, we need the active power, so we multiply this by the power factor. Okay, so we will have 3 V phase I phase power factor. Or you can do another thing, which is power is equal to root 3 V line to line, I line to line, multiplied by the power factor, which is also known as cosine phi. So as you can see, we use the second one, root 3 V line to line, I line, cosine phi. So root 3 V line, which is a line-to-line voltage, 400 volt. I line, which is similar to the phase current, which is 275. And cosine phi, which is the power factor given in the problem, which is 0.8. If you get back to the beginning, you can see 0.8 power factor lagging. This is the power factor of our load. Okay. So this finally gives us that the output power absorbed or output active power absorbed by the load is equal to 15.24 kilowatt. So this was another solved example on the connections or delta Y connections or Y delta connections in the electrical transformer.